Welcome to the third part of lecture. See. So basically, this is lecture 13C. In the previous lectures, we have been discussing sequential logic design. Okay, and now we come to a particular type of sequential logic that is very widely used and it is very powerful, which is called finite state machines, or FSM for short. So, what are FSMs and why are they so interesting? Uh, FSM is basically the control unit of your computer. So you can think of the FSM as a controller which can control the digital circuit. Uh, Finite state machines are useful abstractions. Uh, I think we talked about the word abstraction. Abstraction means to hide details. So FSMs are an abstraction of sequential circuits with centralized states. So it has states or memory. At each clock edge, the combinational logic computes the output and next state as a function of input and present state. So this is a model for FSM. You see it has a combinational logic which is here, and the combinational logic takes an input. This input is coming from the user, and it takes another input which is coming from a register. So this is a register. I think you know that a register is a multi-bit flip-flop, and we have spent some time on the design of flip-flop. So it is a multi-bit flip-flop, and it saves the state of the circuit. So the output of this register is the present state. This in represents the number of bits, so it is an in-bit wide register. And the output of the combinational logic goes outside, so this is our output, and this is our next state. So next state is computed by the combinational logic. So this is a model for finite state machines. Then there are two famous types of FSMs. One is called Moore FSM and the other is called Mealy FSM. Okay, and the difference is here. So if I can just highlight it, for example, with maybe this one. Okay, you see the difference is this direct path. In Mealy FSM, there is a direct path from input to the output combinational logic. So these has particular name. You see, in the previous slide we showed one combinational logic. Here there are two combinational logic. This combinational logic is called next state combinational logic, and this combinational logic is called output combinational logic. Okay, so you see here the output is a function of present state. This is our present state. This is our next state. Okay, this is our present state, this is our next state. Sometimes it is noted by S plus and this one by S. Okay, so you see this one is a function of S and our input. So these are the two types of FSMs. Now let's try to do some examples of designing FSMs. Okay, so let me start with not this one, but I will start with this example. Okay, so the goal is to build an electronic combinational lock. So this is what we want to build with a reset input and two buttons. One button is for inputting 0 and the other button is for inputting 1. So if you press button 0, 0 will be entered to the circuit. If you press button 1, 1 will be input to the circuit. And this is a lock that will only unlock with this sequence. So this sequence is 0 1 0 1 1. So the lock will only open if it sees this combination of inputs. So let me try to we are not covering the Verilog code, we are only designing the lock. So this is called the block diagram. Okay, so you have you only show the inputs and output ports. The next thing is the next design step is called state transition graph or state transition graph STG. Okay, so let's build a state transition graph. So the most important thing to remember when designing the state transition graph is what should be your state. So the most important thing is recognize your state. Okay, so in this example, let's say if as a human I want to implement this kind of code. So imagine if I have some gift, okay, and the person that I have to deliver this gift to is supposed to tell me 01011, and by this code, if he tells me, I will pass on the gift to him, otherwise I will not give him the gift. So in my brain, how I am going to recognize this sequence? So first he will tell me 0, so I will remember that he has told me a 0. Then this 0 should be followed by a 1. Okay, so obviously I have to store the information that he already told me a 0. So it means that I have seen a 0 in a state. Similarly, I have seen a 1 after a 0 is another state. Similarly, I have seen a 0 after a 0 and a 1 is another state. So you see, this is how you would recognize the number of states. So I will start with, let me change the color. So I will start with the first state. Let's say the first state is called SX. SX means unknown state. So in this state, the lock should be 0. So I am using that if unlock is 0, the lock is closed, and if unlock is 1, the lock is open. So you see, here is my unlock signal is U is 0. So I am initially in this state. This is my unknown state, and whenever somebody presses a reset, I come to this state, okay, where this is the initial state and the output is 0. Now if I am in this state and I receive a 1, okay, then my next state is the same as this one. So on a 1 I do not transition because 1 is an invalid sequence. Okay. If I see if I am in this state and I see a 0, so I will move to a state which I can name S0, which means I have seen a 0, but the unlock signal will still be 0. Let me continue with the valid sequence. So if I am in this state S0 and I see a 1, I move to another state. Let me call this state S01. Again, the lock should not open. If I am in this state and I see a 0, I should move to S010 state and the unlock should be 0. If I am in this state and I see a 1, okay, I am just following the valid sequence. Then the state should be S0101 and the unlock should be still 0. If I am in this state and I see a 1, then I should move to the final state in which the output should become 1. So at this point my output should become 1. But you see, this is only the valid state. What I have is, for example, at this state I have the possibility that instead of 1 I receive a 0. So if I receive a 0, I will stay at the same state. Why? Because S0 means I have seen a 0. What if there is another 0? Okay, then it doesn't matter, because even after the second 0 there is a possibility that I see this sequence. So no matter if I see 1 0 or 2 0 or 1,000 zeros, the state will remain the same. Okay, so the state will remain the same. So let me remove this. Now come to a 0-1 state. If I am in a 0-1 state, a 0-1 means I have seen a 0 followed by a 1. So in the valid sequence it is followed by another 0. But what if I see another 1? If I see this 1, okay, what should happen to my sequence? How should my lock behave? So if I see a 1 after I have seen a 0-1, this means that somebody who does not know the code is trying to guess the code. He has entered a wrong code. So on this I should move to the start state. So if I see a 1, I move to the start state. Okay, and in the start state everything will restart from the beginning. Okay, if I am in state 0-1-0, which is this state, so in the valid sequence I have a 1 which is already plotted on the diagram. What if I see a 0? Okay, so I have already seen this state and this is followed by another one, 0. So what should I do? I have two options. Either I go to the initial state as X, or I can also move to another state. Let me draw this in a very different color. I can move from here to here. I have plotted this in green. Why? Because if I see a 0 here, there is a probability that I see a 0, I see a 1 0 1 1 after this. So there is a probability that the valid sequence can be formed. That's why I move to S0 state. Okay, let me remove this. What if I am in S010 state? So I am in I am in 0101 state. So in the valid sequence, the output is the already plotted one is 1. So it means that the left one is 0. So I have the option that what will happen if I see another 0. Now this is very interesting case. Where should I move? I can move to SX state, but I will be wasting so many states, and the other option is I can move to this state, which is 010. So that is very interesting. So on a 0, I move to S010 state. Why? Because after this sequence there is a probability that I see a 1-1. Okay, and if I see a 1-1, this will be my valid sequence. Okay, for both these green and black curves, they can go to SX. Okay, those kinds of FSMs are called non-recurring FSMs. If I go to SX, those are called non-recurring, and the one we are drawing here is called recurring FSM. Okay, it is recurring, it is repeating itself, it is repeating the states in search for a quick path to form the valid sequence. Okay, let me come to the final one. So if I am in state S0111, okay, what will happen if I see another one? Okay, so from here the lock should come to the initial state, which is this one, because this one cannot be the first bit of a valid sequence. This cannot be the first bit of a valid sequence because the valid sequence starts with a 0. Okay, what will happen if instead of 1 I see a 0? So where should we go? Again, if this is a non-recurring FSM, we should go to SX. But if it is a recurring FSM, then this 0 can be the first bit of the next valid sequence. In that case, I have to move to this state, which says I have seen a 0. Okay, so this is how state machines are formed. This is one example of a state machine. On the next slide, this is the top level diagram, let's say, of if you want to implement this in a lab. So this is our FSM for 011. Okay, and these are some other circuits that are required. We will discuss about this circuit. This circuit is called synchronizer. We will discuss about this synchronizer buttons, and this is 7-segment display, and you can attach the unlock signal to an LED. So if the LED turns on, you will see it is unlocked. If it is off, it means it is locked, and the internal state can be observed on a 7-segment display. So maybe in the next course you will be working with FPGAs. this may be one of the labs. Okay, so again this is the FSM state transition diagram that I have drawn. So this was my SX state, this is my S0 state, this is my S01 state, this is my S010 state, this is my S0101 state, and this is my S01011 state. So I have drawn it by hand so that you can understand all the steps very easily. So you have to practice with several examples. Let me come to another example. So this was the point at which I left off for the second example. Now let me go through this example. I think I will defer this example to the next week, as this week lecture has already been recorded for almost 2 hours or something. So I think we will go through this second example in the next lecture. Okay. Okay, so we started with the topic of FSMs, and in the previous lecture we have designed an FSM for detecting this sequence 01011. So I will just skip these initial parts. So it is basically the whole block diagram. This is for if you want to implement this in a lab. So this is our FSM, and then we have several other things at the output, for example 7-segment display, and then we have these buttons and these modules. Okay, so I will talk about this in the coming slide. These are called synchronizers. This is clock generators. So this is coming from a crystal oscillator. We have already seen how to design the bubble diagram. In this lecture we will see how we can take the bubble diagram and we can generate a logic circuit. So we will see this transformation in this lecture. So this is just a repetition of that lecture. So this was the FSM that we designed. So after this FSM, I expect that if I gave you another problem, for example, if I gave you to detect this sequence 111, and remember that I explained two flavors. One was recurrent FSM, and the other one was non-recurrent FSM. So you should be able to design these two FSMs for any problem. These problems, this category of problem is called sequence recognizers. So this category of problem is called sequence recognizer. This is one class of problems to which FSMs can be applied. Let's come to another example which is quite interesting. So imagine that you have a digital system. So this is our digital system, and this digital systems runs at a clock frequency of 100 megahertz. Now here is a user. Okay, this is you, for example, and this user wants to give an input to this system. Now if you think about this, the user is giving an input that is asynchronous. It is not synchronized with the clock. Okay, and this can become a problem. For example, imagine that we started in the previous lecture with a problem that a user wants to push a button. Now, if the user wants to push a button and maybe he push it for 1 second, okay, but in this 1 second, how many cycles are there for the digital system? The digital system will have 100 these cycles, so it is basically 10 power 8 cycles. So in 1 second, so many times the system will be triggered, but actually you want that the user inputs only once, not multiple times. Now this is a problem. Okay, so how we should interface an asynchronous user with a synchronous system? We need what is called a level to pulse converter. So this is that block. We need it here. We need a level to pulse converter. And what this device does, it is very interesting device, that if you have this kind of level, so this is a level input, what this system does, it takes the same 100 megahertz clock frequency, but it converts this level input to a pulse that is exactly 1 T clock. That is exactly 1 time period. How can we develop this interesting system? So let me tell you, this is a finite state machine, and just to revise, a finite state machine is the combination of combinational logic and sequential logic. Okay, so you have these outputs and next state at the output of this combinational logic, and then you have present state and input to this combinational logic. So basically these registers, they store the state of system. Okay, so let's try to and then there are 2 types of FSMs. I think we also discussed this. I will just quickly go over them. One is called Moore FSM and the other is called Mealy FSM. So in Moore FSM, the output is a function of present state. So output is a function of present state only, while in a Mealy FSM, the output is a function of present state and input. So you see this additional direct combinational path coming from the input to the output combinational logic. So this is called output combinational logic, output combinational logic. This is called next state combinational logic, next state combinational logic. Okay. This is called next state because it produces the next state. So S plus is the next state. Okay, so let's come to this design again of the level to pulse converter, and just a reminder on synchronizer. What is a synchronizer? As I told you before, these buttons. So this button, basically if I expand it, this button consists of two things. One is a synchronizer and the other is a level 2 pulse converter. Now let me explain the need of these two. You already have came to know that level 2 pulse converter is to convert the input from a user which can span multiple clock cycles, and the level 2 pulse converter converts it into exactly one clock cycle. So what is the function of a synchronizer? A synchronizer is there to handle meta stability. If you remember, when we were designing the flip-flop, we discussed the problem of metastability, and we said that the earlier computers used to hang a lot because of metastability. Okay, so when a user is giving an input, so this is the synchronizer circuit, this is the synchronizer, this is one piece of the button module that is inside that digital lock. So imagine that this is our push button and a user can push it like this from top and it generates this level. So what you do, you put several registers, R1, R2, R3. These registers are called synchronizers. The registers are connected in a pipeline fashion. So the output of one is the input of another. Okay, and you only pass your asynchronous input. So this is your asynchronous input. You first pass it to 2 or 3 synchronizers. So what synchronizer does? It reduces the probability of metastability. Okay, so synchronizers reduces the probability of metastability. And just to remind you what was metastability, so if you had this back-to-back inverters, we saw that there was this curve. This was for our buffer, and then there was this is for inverter. So we had this kind of curve for buffer, and then we had this kind of curve for this feedback path, and we said that it intersects at 3 points. 2 of them are stable and 1 is metastable. And if your system goes to this metastable state, your digital system will be confused and it will not be able to understand if it is a 0 or a 1. Okay, so the danger of going to this state, metastability, increases if a asynchronous input is coming to your digital system. So remember, you always put synchronizers at the interface between asynchronous inputs and your digital systems. This is very important. Otherwise your system may go metastable. So imagine that you are interacting with your computer through your keyboard. So the keyboard is an asynchronous input. So every button of your keyboard, at the back side of this button you have a circuit which has 2 components. It has a synchronizer and it has a level 2 pulse converter. So these both are present in your keyboard circuit. There is also a third
part that is called the bouncer, but let's not go there. So just consider these two. So how can a system become metastable? When asynchronous inputs are fed to it. So imagine this is our D input, and this is our system. So this is our Q1 and this is our Q2, and here comes an asynchronous input D1. So what can happen that on the first clock cycle it may be caged by Q1. So Q1 catches it, but Q2 does not catch it. Okay. Then for example, consider the other case. It may happen that this transition happens here, but it is captured by Q1 after some time. Okay, because it may miss it on this clock cycle. Okay. What can happen in this case, for example, that here is our Q1 and here is our clock. So when the clock goes and samples our D input, it is in the middle between 0 and 1. And when it is in the middle between 0 and 1, your system Q1 goes metastable. Okay, so you do not want to sample at this point, which is in the forbidden zone. So the only way, if you want to avoid metastability, the only solution is to wait. Okay, is to wait for noise. So imagine that a metastable system is like this. You are trapped on this, in this middle point. So this is your metastable state. You have to wait there until a noise comes. Remember that you are in a very high amplification region. So you are in a very high amplification region, and even a little noise can take you to logic 1 or logic 0. So the only way to solve metastability is to wait for noise. And these synchronizers, and what are these flip-flops doing? They are, the first synchronizer introduces a wait of 1 cycle. So the other one introduces a wait of 1 more cycle. So overall, here you are waiting 2 cycles. Whenever you insert a flip-flop, you are introducing a delay of 1 cycle. So if you want to reduce the probability of metastability, you can increase the number of flip-flops in your synchronizer. Okay, now let's come to our level 2 pulse converter. So we put 2 flip-flops as a synchronizer on the input. Then we want to design this level 2 pulse converter or edge detector. So I told you the most important difficulty that students find in designing FSMs is what should be the state. So imagine that you have this level as your input. Okay, so this level is your input, and this is our clock signal coming. So this is our positive edge, positive edge, positive edge, positive edge. So what are the options? What are the states? First option is that on a clock cycle I go and I check the level and it is 0. I check again and it is 0. I check again and it is 1. I check again and it is 1. I check again and it's 1. So what should be the states? One state could be the input is 0 or input is low. So this is just a name. And when the input is low, what should be your output? The output should be perfectly 0. Okay. But when there is a change from 0 to 1, what you do, you convert your input, your output from 0 to 1. But on the next one, so if this is the first time you consider a 1, and this is the second time you encounter a 1, on the second one you drop your output to 0. Okay. So you have basically 3 states. One state is this, in which the input is low. One state is this, in which the input is high. And then there is a third state, that is the edge state. So we have 3 states. Input is low, edge state, and input is high. Okay, so we have 3 states. We have successfully recognized there are 3 states. And you have to remember that in Moore FSM, the output is represented in the bubble inside. So here the output is 0. We see the output is 0. When we are in the edge state, so this is the edge state, the output is 1. And when we are in the high state, the output is 0. P is 0. Okay. So we have these 3 states. So what happens if we are at the input state? Okay. Input is low state, and we see that the level is 0. So imagine we are talking about, this is our first clock cycle, this is our second clock cycle, this is our third clock cycle, fourth and fifth. So we are talking about the first clock cycle. Okay, let me write it inside. So this is the first clock cycle and second clock cycle. For both these cycles, we stay in the same state, which is input is low. We are waiting for a rise. We only go out of this state to the next state when we go and check that our input has become 1. And this is the third cycle. Okay, so if you go and check on the third cycle, you see that the input has become 1. So you move from this state to this state. Okay. Now if you are in the edge state and you go and check the input again and it is 1, so we are talking about the fourth cycle. And in the fourth cycle, what happens, that your output should be low. So we move to the next state and we say the output is 0, and we name the state input is high. So this is the fourth cycle. Now in the fifth cycle, 6 cycles, and it goes on and on. In all these cycles, it doesn't matter how many cycles we have, the system will remain in this state. It will loop here. because the output for all other cycles, 5th, 6th, 7th, 8th, 10th, 100, 1000, 10,000, 1 lakh, it will always be 0. Okay, you only go out of this state when you encounter an L is equal to 0. So on an L is equal to 0, maybe after 1000 cycles the input has become 0. Okay, so then you go to input is low. So we have successfully discussed this line, this line, this line, this line, and this line. One interesting line is remained to be explained, and that is this line. What this means, what is mean by this line? This line means that imagine that there is a user which is providing a pulse, and he is so fast that if you consider the clock, he is so fast that he is able to provide your input. So this is our pulse input so quickly that his pulse is exactly 1 cycle. So this is just an imaginary scenario, because no one is fast enough to press a button and leave it in 1/100 megahertz. Okay, so this is that theoretical case, but nobody can do it. But your FSM should be complete. By complete, it means that if your input is 1 bit, for example in this case the L is 1 bit, then each state should have 2 arrows for L is equal to 0 and for L is equal to 1. So I hope that you understand this FSM. This is called Moore FSM. Okay, so this is some detail about the properties of the arcs, as I told you. Now the next step in converting is your FSM. So you have this bubble diagram. You have to convert this bubble diagram to a logic circuit. And how we do it? We have to choose a state representation. We have to code the states. This is called state encoding. So one option is binary encoding. Okay, in binary encoding you just check that if there are 4 states, then you need 2 bits, because 2 power 2 is 4. If there are 6 states, then you need 3 bits. Okay, so this is binary encoding. Then one hot is different. If you have 4 bits, then you need 4. If you have 4 states, then you need 4 bits. So the number of bits is equal to the number of states. These two have different properties. For example, this one has a lower power consumption, because in this one, you remember in the power consumption chapter we discussed the switching activity. The switching activity is low in 1 hot encoding compared to binary encoding. And if you want to reduce the switching activity, you have to ensure that only a single bit changes. If 2 bits changes, then your switching activity is higher. So 1 hot encoding is a scheme in which if you go from 1 bit from one number to the next number, only a single number change and only a single bit changes. But in binary numbers, if you go from one number to the other, multiple bits can change. Okay, and this multiple change of bits mean higher power consumption. So let's go through the details of converting our level 2 pulse converter into a circuit. So we start with the state encoding. We can, because we have 3 states, so we have 1, 2, 3 states. This is 1, this is 2, and this is 3. We need 2 bits. So let's encode it. The first state we encode as 0, 0. The next state we encode as 0, 1. The next state we encode as 1, 1. So these are our 3 states. Next thing is we develop a sort of truth table. Okay, this is something like this. You have on this side we have the current state, and as we see we need 2 bits, S0 and S1 for the current state. And then we have our input. So this is our input side, and our input is just the level. On the output side we have the next state. It is represented by S0 plus S1 plus, and we have the output. Now it is very easy to convert this bubble diagram, okay, to the state. For example, consider the first circle. In the first circle, the present state is 0, 0. So it is here, it is 0, 0. And if we are talking about the input L is equal to 0, L is equal to 0 is this. What is the next state for L is equal to 0? The next state for L is equal to 0 is again 0, 0. So we remain on the same state. And what is the output? The output is P is equal to 0. So this completes one entry of our table. The next is if our present state is 0, 0. So again we are talking about the first bubble, and our input is 1. So we are talking about this line. What is our next state? Our next state is 0, 1. And what is our output? Now it is important to note the output, because this is a Moore machine, the output is dependent on the present state. So we will write the output from this one, from bubble 1, and not from bubble 2. Okay, so this completes the first state and its 2 arcs. Then we go to the next state for which these 2 lines are there. Then we go to the third stage for which these 2 lines are there. I hope that you can understand these lines. And forming the equation is very straightforward. For example, if I ask you what is the equation of S1 plus, what is the circuit for S1 plus, so you can easily see that it is 1 where it is 1 when S1 is 0 and S0 is 1. I am talking about this line. I'm talking about this line, and it is 1 when we have this combination plus S1 is not. And you can simplify this if you take S0 common, so it will be there is a third term in this equation, which is this L. So the first term is S1 bar S0 into L, so this one, and the next one is S1 S0 L. So what you can do, we can take S0 and L common, and inside we will have S1 bar plus S1, and this is equal to S0 L, because S1 bar plus S1 is 1. So this is the equation. Similarly, you can write the equation of S0 plus, which is this one, L. You can write the equation of output, which is 1 1 here, and this is P0 P is equal to S1 into S0 bar. So these are your three equations, and if you draw it, it is like this. The circuit is like this. You have two states. This is the present state, okay, present state, and because we have 2 bits, we use 2 flip-flops. This is flip-flop 1, flip-flop 2. Then the output, the equation for the output was S0 S1 bar. So we connect this to Q prime and this to Q. So this is our output. And what were the equations of next state? The equation for S0 plus was only L, and the equation for S1 plus was L N2. You see present state, so this is S0, so L N2 S0. You see this red, which is a feedback. So this is the complete circuit for our level 2 pulse converter. You see, this is a very small circuit, and this circuit is very beautiful circuit because it takes a level and it converts it into a pulse. This small circuit is needed whenever an asynchronous input has to be fed into a digital system. So this is very important small circuit. Now you can also design a Mealy FSM. Remember that the Mealy FSM has this direct path to the output combinational logic. So the output combinational logic was a function of present state and input. Okay, so in this state, in this case, we can have only 2 states. Input is low and input is high. So remember that in a Mealy FSM, in most of the cases, the number of states will be less than the Moore FSM. In most cases, only it will be less by 1 state. Okay, and the reason for this is this one, that we represent the output on the arc and not inside. So the output is not here, it is on the arc. So which means if you are in the input is equal to low state, okay, and you receive an input of 0, your output is 0 and you remain in the same state. If you are in this state and you receive an input of 1, you directly change your output from 0 to 1 without waiting to go into the next state. Okay, that is what is mean by output is a function of input plus present state. So whenever your present state, the tail of the arc is your present state, the head of the arc is your next state, but the output changes on the arc, okay, not at the tail or the head. Okay, so that's the difference between a Moore and a Mealy FSM. So you go to input is high. Now if you are in this state and L is equal to 1, then P is equal to 0 for infinite number of clock cycles. It doesn't matter how many cycles it passes, but as long as the input is 1, the output is 0. You only move out of the state when you go and check that your level has become 0. So this is Moore FSM. Okay, so if you consider this, the Moore FSM is one cycle faster, okay, and it has also one less state. But there are certain disadvantages to this, that we will see that the combinational logic can glitch, okay, it can have unwanted transitions. So if you want reliability, if you want that your system should work always, go for Moore FSM because it is more reliable, and Mealy FSM can subject to glitches. So again, we can convert this into this circuit, this and this. I recommend you to go to this through this truth table and how the circuit is generated. So these are the trades of Moore FSM and Mealy FSM. Moore is more reliable, Mealy is faster, one clock cycle faster. Also the number of states are less. But if you want to be 100% sure, then use Moore FSM. Now from where the clock comes, this is just a slide that is, let's say, about the clock to the FSM. So the clock should come from, it can come from external crystal, this is one option. It can come from an internal signal, so the combinational logic, but in this case it can glitch, okay, but it is always safe that if you have a digital system, then it should follow this methodology, that you have a register, then a combinational logic, and then another register. Okay, so always do like this, that if you have your combinational logic here, always put a register there. Okay, so this is basically for Mealy FSM. You see the Mealy FSM, the output is directly combinational logic. So if you want, you can add a register here, and this register will synchronize this output to the next digital system. Okay, so if you think about it, if you want to remove the limitation of reliability from Mealy FSM, you have to put an extra register there, extra reg for reliability. Okay, so again it becomes the same story. It's better to design a Moore FSM. It's better because most of the people find it easy. Moore FSMs are easy to design, but it's your choice. You can design Mealy FSM, you can design Moore FSM. So this is the end of this lecture. I hope that you will practice on several other examples for FSMs. We will also come back to the FSM topic when we discuss memories, particularly ROMs, and we will see how we can implement an entire FSM on a ROM.